In section 3.3, we're going to begin writing functions. So the warm-up asks us to evaluate each expression or find the value of each expression, given that a equals 2, b equals -3, and c equals 8. So we're going to simply take our a, b, and c values, plug them in, and use PEMDAS to evaluate. So take a minute to check your solutions, the values of each of these expressions. Be careful in number 5. When we are squaring a negative number, it means we're doing -3 times -3, which is a positive 9. So our goals for today are to be able to identify independent and dependent variables, and to write an equation in function notation and evaluate a function for given input values. So we've got a couple vocabulary terms here. We have independent variable, which is the input or the x value of our function. It controls the dependent variable. The dependent variable is the output or y value of a function. It depends on or is a function of the value of the independent variable. So whatever happens with the independent variable directly impacts and makes a difference in what the dependent variable ends up being. A function rule is an algebraic expression that defines a function, that defines the relationship between our independent and dependent variables, or x and y, our inputs and outputs. Now, function notation, f parentheses x, is literally read f of x, where f names the function, x is the independent variable, and y is basically the same thing as saying f of x. So f of x is a fancy version of saying y, and that is the dependent variable. So our first couple problems, we're going to try to determine a relationship between our x and y values. So we're just going to try to think, okay, do I add or subtract the same number from one x to get to its y, the next x to get to its y? Or am I multiplying, dividing by something? Maybe I multiply and then do some addition or subtraction. So if you look at the table written here in the model, we have the x values of 5, 10, 15, 20, y values of 1, 2, 3, 4. So both of them are kind of following a pattern. But we need to study and look at what's happening between the x and its y. So hopefully you see that our x values are all multiples of 5. So if I take my y value and multiply it by 5, I get my x. Going the other way around, if I take my x and divide it by 5, I get my y. So what we want to do is we want to perform our operation on the x value. Okay, so because we see a common multiple here, okay, we're going to say, all right, y is equal to x divided by 5. Also equivalent to saying 1/5 times x. Okay, there is a little sample here of also trying to determine if we were adding or subtracting, but due to the fact that we had that common multiple here happening, we were definitely looking at some sort of either multiplication or division. So let's take a look at number 1. So what do we have to do to x in order to find y? So we've got an ordered pair 1, 3, an ordered pair 2, 6, an ordered pair 3, 9, and an ordered pair 4, 12. So let's first check to see if I can add or subtract the same number from x to get y. So in the first ordered pair, to go from x to y, it was add 2, right? Because 1 plus 2 is 3. But then the second ordered pair, to go from 2 to 6, you have to add 4. Then to go from 3 to 9, you have to add 6. To go from 4 to 12, you have to add 8. Okay, so due to the fact that we're not adding the same amount to our x every single time to get y, it's not addition. So let's look at multiplication. Well, 1 times what number is 3? Well, 1 times 3 equals 3. What number times 2 gives us 6? Well, 2 times 3 gives us 6. What number times 3 gives us 9? 3 times 3 gives us 9. And what number times 4 gives us 12? 4 times 3 gives us 12. So we did the same thing to every x value that was listed here. We took our x value and we multiplied it by 3 to get our y value. So let's state that. We took x and we multiplied it by 3 and we got y. So let's write it as a nice equation now. Y equals 3x. Now technically in example 1, we technically did have a function because for every x value there was one y value. For every input there was one output. Now let's talk about independent versus dependent variables and how we figure out which relies on which. So the input of our function, the number that's going in, is called the independent variable. The output of a function is called the dependent variable, so the result of plugging in the input and doing the math. That would therefore mean that the dependent variable depends on or relies on and therefore is a function of the value of the independent variable. So we have a model here that says a painter must measure a room before deciding how much paint to buy. We want to identify the independent and dependent variables in this situation. So do we determine room size by the amount of paint we want to buy, or do we determine the amount of paint we need to buy by knowing the room size? Okay, so our dependent variable is the easiest one to identify first. That's going to be the amount of paint we need. The amount of paint we need literally relies on the size of the room. Okay, so the size of the room, measurements of the room would be the independent variable. Therefore, the dependent variable is the amount of paint. So if we look at number 2, it says the height of a candle decreases d centimeters for every hour it burns. We want to identify the independent and the dependent variable. So we're talking about the height of a candle as a result of how long it's burning. If you burn a candle for 5 minutes versus 5 hours, there's going to be a difference in the height. So that means the height relies on or depends on the amount of time that the candle was burning. Okay, so the dependent variable is the height or the amount of decrease. And that relies on the time that the candle burns. Next, we have number 3. A veterinarian must weigh an animal before determining the amount of medication. We need to determine our independent and dependent variables. Now think about which has to come first. Or think about 2 different types of dogs. Think about a tiny little Yorkie versus a huge German Shepherd. Would they require the same amount of dosage of, say, flea and tick medication, where one is tiny and one is huge? Well, no, it's going to vary based on the size of the dog. So the amount of medication depends on weight of dog. So our dependent variable is amount of medication, whereas the independent is the weight of the dog. Number 4, a company charges $10 per hour to rent a jackhammer. What's our independent and dependent variables? Well, if we're talking about $10 per hour, we're then going to ultimately pay a total amount for the service. So the total amount of the service relies on how long it is that the person is using the jackhammer. So the dependent variable here would be the total cost. That would be our output. And that relies on number of hours, or the time. that the jackhammer is being rented. Number 5 is the same idea as number 4. So go ahead and let me know if we are comparing pounds and cost as our two different variables, which is my independent and dependent variables. So once again, and like many scenarios, the dependent variable is going to be the total cost, and it relies on how many pounds of apples you're purchasing. 4 and 5 are getting a little bit more specific because it's giving us a rate for per hour for number 4 and rate per pound of apples in number 5. So then we're going to actually be able to literally write an equation or a function rule for numbers 4 and 5. Now, a function rule is an algebraic expression that defines a function. So, for example, if Tasha earns $5 for each hour she babysits, then we would use 5 times x as our function rule to model her total earnings, because we could also view it as $5 per hour. So we'd be multiplying 5 times the number of hours. If x is the independent variable, because it can vary or change, then y is the dependent variable. Okay, so y is the total amount she's bringing in. And then because function notation, we use f of x instead of y, we would write this function as f of x equals 5x, where x represents number of hours, because it's $5 per hour. And the final result, that output, is going to be the total amount of money that she earns. Okay, and again, f of x is just a fancy way of saying y. So if you want to start off by saying y equals 5x, that's fine, but then we're going to call y f of x. Okay, so now we're going to start tying some numbers to these situations. So number 6 says that a fitness center charges a $100 initiation fee plus $40 per month. Okay, so we see that word per, and it's months. So it's almost easiest to write our expression that it's $40 per month, so we're going to multiply 40 times m, and then we're going to add our initial cost of $100. And what we get as a result is the total cost. Now in this particular case, the variable tied to the 40 is going to be our independent variable. The number of months that we are a member, okay, will then determine the total amount of money that is paid. Okay, so our independent variable is going to be months, whereas my dependent variable is going to be the total cost. So because I'm going to use my variable m to represent months, I'm going to use the function c of m. And write then our expression is equal to 40m plus 100, where our m equals number of months. And technically c of m is equal to the total cost. So the C kind of referring to cost based on m number of months. Number 7, Stephen buys lettuce that costs $1.69 per pound. So the number of pounds that is purchased will be our independent variable, and that will determine how much we're spending on lettuce. Okay, so our dependent is going to be total cost, which relies on our independent variable, pounds. So I'm going to, let's go over to the side just like we did before. If it's $1.69 per pound, it's going to be 1.69 times, I'll use X this time because I don't want to use L, because an L looks like a 1 or an I. We could use P, but I'll just use X. So 1.69 times X is going to equal our total cost. So because I use my variable X, I will just use f of X for my function notation as my total cost. So f of X, the total cost is equal to doing $1.69 times the number of pounds. Okay, so let X equal number of pounds, and then the required part of the let statement is the first line. The second piece that I'm writing is just to help you see what it is our output or our y value, our f of x, c of m, g of x, whatever it may be, what that actually represents. So our f of x in this case equals our total cost relative to the number of pounds that are put in. Number 8, an amusement park charges a $6 parking fee plus $29.99 per person. So again, we've got that word per, so we've got a slope here, a rate of change, multiply. So the amount that you have to pay depends on how many people you're taking into the park. So my dependent variable is going to be my total cost again. And my independent variable is number of people, because that's going to be what's multiplying by the 29.99. That's going to be our fluctuating input. So number of people. Because that $6 parking fee is a flat fee no matter what. So we have to pay $6 plus an additional $29.99 times the number of people in order to get total. So because I used X for my independent variable, my function, I'm going to be jazzy. I'm going to use g of x. So f of x is the most common. Okay, that is the most common way of showing our function notation. However, g of x and h of x are also common ways to represent a function, and then other variables based on the situation. So I'm going to use g of x, which is the same thing as f of x, which is the same thing as y, and in this case represents our total again. So g of x is equal to, I'm going to put my variable first, $29.99 times x plus 6, where in this case our x equals number of people, and then the side note is that g of x then tells us our total cost. So once you have a function that's written, you can take any number or value for your independent variable and plug it in to figure out what that ultimate output or dependent variable will become. So we need to work on showing good function notation and not be scared of it. So these examples say to evaluate the function for the given input values. So this is, in number 9, we have the function f of x equals 3x plus 2. We want to find f of x when x equals 7 and when x equals negative 4. So what we need to do is we need to take 7 and plug it in wherever we see an x. So we're going to find f of 7 and say it's equal to 3 times 7 plus 2. So this means the function value when x is 7 is equal to 3 times 7 plus 2. So we PEMDAS now. So f of 7 equals 21 plus 2. So f of 7 equals 23. Okay, so this literally means when x equals 7, y equals 23. Okay, so it can also be represented as the ordered pair 7, 23. For the second part, we're plugging in -4 for x. So we're going to redo the problem, this time plugging in -4. So f of -4, showing we're plugging -4 in wherever we see an x, is equal to 3 times -4 plus 2. So f of -4 equals, following PEMDAS, 3 times -4 is -12 plus 2, and -12 plus 2 is -10. So f of -4 equals -10. So using our nice function notation, that's our answer. That's how we write it. This also translates to when x equals -4, y equals -10, which is also equivalent to the ordered pair -4, -10. Okay, we need to be comfortable going back and forth here. Let's do number 10 together. For g of t equals 1.5t minus 5, find g of t when t equals 6 and when t equals -2. So we're going to start off with the first one, plugging in 6 for our variable t. So we're going to show g of 6 equals 1.5 times 6 minus 5. We need to PEMDAS. So we have to do the 1.5 times 6. So g of 6 equals, that's going to give us 9. Drag down the minus 5. So g of 6 equals 4. Okay, so when t equals 4, when t equals 6, g of t equals 4. Okay, when x is 6, y is 4. So even though we're using completely different variables, the input, okay, is always going to be referred to as what we would call the x. Okay, so 6, 4 would be equivalent. Now let's plug in -2. So g of -2 equals 1.5 times -2 minus 5. PEMDAS g of -2 equals 1.5 times -2 is going to be -3. Drag down the minus 5. So g of -2 equals -8. So when t is -2, g of t equals -8. So when x is -2, y is -8. So I would like you to go ahead and complete numbers 11 and 12 using 9 and 10 as a reference. So hopefully we got h of 1 equals 1 when x is 1, y is 1. H of -3 equals -7. So when x is -3, y is -7. Number 12, h of 600 equals 202. So when x is 600, y is 202. And h of -12 equals -2. So when when x equals -12, y equals -2. And finally here, to wrap things up, we're going to bring in a real-life situation. And sometimes when we're dealing with our real-world situations, we can't necessarily use every real number as a reasonable domain and range. So, for example, when we're talking about numbers of people, numbers of DVDs, things like that, it's only going to be whole numbers. And also length of an object, it can't be negative. So there's a lot of things that come into play that sometimes we need to use a little bit of logic. And whenever we're talking about, okay, we're only using whole numbers, perhaps we're going to be dealing with our discrete situation. So we're not going to necessarily be connecting those points. Okay, so here's an example that says Joe has enough money to buy 1, 2, or 3 DVDs at $15 each if he buys any at all. Write a function to describe the situation. Find the reasonable domain and range of the function. So the total money spent is going to be my y value, my output, my f of x. And that's calculated by doing 15 times the number of DVDs purchased. And again, like here's a situation where you can't buy 1.5 DVDs. Okay, so each DVD is $15. He's going to buy 0 DVDs, 1 DVD, 2 DVDs, 3 DVDs, 4 DVDs, heck, maybe 10 DVDs if he's looking for a movie marathon. Okay, but this is definitely a discrete situation where we're only talking whole numbers. Okay, so if we were graphing this, we would not connect the ordered pairs. So the domain here would be 0, 1, 2, 3, and could potentially go on farther, although this particular question only goes up to 3. And then its corresponding range would be $0 for 0 DVDs, $15 for 1 DVD, $30 for 2 DVDs, and $45 for 3 DVDs. So if we look at number 13, it says the settings on a space heater are the whole numbers from 0 to 3. Okay, so based on how high the number is, that's going to be the actual heat, how high, relatively speaking, the heat will get. So the number of watts used for each setting is 500 times the setting number. Write a function to describe the number of watts used for each setting. Find the reasonable domain and range for the function. So the settings are only 0, 1, 2, and 3 because we're saying whole numbers from 0 to 3. So that's going to be my x. It's my domain. Oops, I can't talk and write at the same time today. 0, 1, 2, and 3. Now, what happens then as a result in terms of the actual heat if we're talking setting of 0, setting of 1, setting of 2, setting of 3? So we need to write our function. It says the total number of watts. Okay, so total is 500 times the setting number. So 500 times setting. And the setting number is our x. So f of x equals 500 times x, where we let x equal setting number and f of x equals total watts. So we need to take the x value of 0, substitute it into our function to figure out how many total watts. So we're going to find f of 0. So we do 500 times 0. So f of 0 equals 0. Now we're going to plug in 1 for x. F of 1 equals 500 times 1. So f of 1 equals 500. Next we have to do f of 2. So hopefully you're seeing a pattern, 500 times 2. So f of 2 will be 1,000 watts. Okay, so when x is 2, y or f of x is 1,000. And f of 3 is 500 times 3, which means f of 3 equals 1,500. Which therefore means that our domain is these x values, okay, our input of 0, 1, 2, and 3. And then our range is our output, our function values, the y values, of 0, 500, 1,000, and 1,500. Okay, and nothing in between because they're only whole numbers from 0 to 3.